All right, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. The same rules and logistics I have been saying for every DDPS seminar. Okay, first of all, please mute yourself during the talk. But if you have questions, you can unmute and ask questions, or use chat room to post your questions so that we can address them in Q&A session. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor, it's a great honor to host Dr. Doug James, who is a professor of computer science at Stanford University and a member of Stanford's Center for Computer Research in Music and Acoustics and the Institute for Computational and Mathematical Engineering, ICME. He has been a consulting senior research scientist at NVIDIA Research since 2022. He holds 3 degrees in applied mathematics, including a Ph.D. in 2001 from the University of British Columbia. In 2002, he joined the School of Computer Science at Carnegie Mellon University as an assistant professor, and later became an associate professor of the computer science at Cornell University. His research interests include computer graphics, computer sound, physically based modeling, and animations and reduced order physics models. Doug is a recipient of the National Science Foundation Career Award and a fellow of both the Alfred Sloan Foundation and the Guggenheim Foundation. He received the ACM Seagard 2021 Computer Graphics Achievement Award, a 2012 Technical Achievement Award from the Academy of Motion Picture Arts and Sciences for the Wavelet Turbulence, and the 2013 Katayanagi Emerging Leadership Prize from the Carnegie Mellon University and Tokyo University of Technology. He was the Technical Paper Program Chair of ACM Shigar 2015 and a consulting senior research scientist at Pixar Animation Studios from 2015 to 2020. All right, today Doug will talk about recent progress in reduced order modeling for computer graphics and sound. I'm sure he's going to give a great talk, no doubt about it. So please be prepared. Now, let me ask a question to Doug, just to make this stage somewhat informal. Is it okay to ask some question, Doug?
Yeah, please, by all means, ask questions and at any point. I'm gonna go through a lot of material and think of the talk as kind of an advertisement for the material, like you find the details in the paper. I just don't have time to go through everything, but by all means, if you have questions, just shoot.
Which is fine. Okay, the first question is even before you give a talk.
Okay.
I see that you are passionate not only the computational science, computer science, but also the music. And if you can share your favorite music piece with us.
Wow. Yes, I mean, I love I guess I love all the things related to sight and such, touch and sound, and how that relates to math and physics, and it's sort of always been one thing together, I don't know. How about Paul Gilbert's Curse of Castle Dragon? Put that on if you want to get your energy levels up. That will get you going in the morning.
Awesome.
Anyway.
Okay. I don't know of that music, but I will definitely try.
Yeah, amazing guitarist.
Okay. Thank you. Stage is yours.
Okay, great. So thanks for coming to the talk, everybody. So I've always been excited, for the last 20 years about reduced order modeling, about how to make things fast by doing things in low dimensions, speeding up dynamics of deformable models, allowing that to be used to do faster GPU rendering of the models, the motion, and being able to use reduced order representations for faster collision processing, contact processing, supporting haptic feedback at kilohertz rates, and even sound without having to deform everything. So, reduced order models, I just love them. Some things you have to, you need full dimensions to do if you want a lot of details or things that you haven't seen before or don't know what the basis is. And so that kind of leads to the first part of the talk. And the second part is going to be about fluids and the sounds that water makes and how to compute those using reduced order models. So let me see how to do this. Okay, so I guess I want to start by thanking my PhD students. So this is work by two amazing PhD students. The first one is Eris. Eris has done a lot of incredible work on simulating deformable models, and that's related to the progressive physics or progressive methods that she developed. That's the first part of the talk. The second part is by Congre. And Congre has been working on doing fast simulation of fluid sounds and also GPU acoustics and things like that to basically make the simulation of everything we can visually animate also have sound in a practical way. So that's like the future includes sound that's a first-class physical primitive. Okay, so to start with, this is the work on progressive simulation. So the basic idea is that we want to be able to compute things, resolution progressive way. And this work was with a number of amazing collaborators. So in particular, Danny Kaufman at Adobe. It also started out with Alec Jacobson and Raymond and others. And so this is something that she's been working on for a few years now, and it's really coming along. The motivation is basically you have, maybe you want to do design. So if you have a scene like this, you want to have like cloth and you want to lay things out to do set design or to make a scene in a 3D modeling tool. So there's all kinds of materials, there's contact. Maybe you want to have cloth and shells in these sort of environments. And being able to manipulate physical models is really tedious. It's often very, very slow. So you have this basic problem of speed versus fidelity, which, this is a reduced order modeling session. So this is the basic story, right? Like you want it to be good, but you also want it to be fast. And there's a trade-off that you have to make and a lot of fun math to keep us employed. But currently we can do stuff like this. You can pull on a piece of cloth and then it can respond in real time. Maybe it's on like a GPU or a CPU, whatever. There's some amount of parallelism that can be employed. But you can't really make it's cool that it does this in real time, but it's also limited. The other kind of things we have to deal with are the simulators have all kinds of limitations. So on the left, we have like a, animation production quality system, Houdini, which allows us to simulate this cloth, but it's got jittering artifacts, it's got intersections, maybe it has other problems depending on your parameters that you didn't tune expertly. On the right is like the state-of-the-art in cloth design tool, Close Marvelous Designer. It has all these fantastic materials, but it's not stable and maybe it'll blow up in some cases, so you try again, right? So how do you get all of these things, how do you get reliable simulations that are also fast? Here's like a state-of-the-art simulator based on incremental potential contact, which is kind of like a, full-blown elasticity solver with barrier methods that are robust and allow you to make sure it'll always work and not die. But it may take a long, long time to get these results. So minutes per frame or, hours per simulation, but you'll get something good. But how do you design or work with that if you're trying to do design or animation? So the other thing that's really important is control. And so it's not just it's not just speed and fidelity. The point is you want to use this for art-directable physics. You want to design something, you want to make a movie, you want to do something with a human in the loop. But if it's so slow, you can't do it, or if it's no good, it doesn't matter. So here's a shot from Incredibles 2 that I know some people at Pixar spent a lot of time thinking about. like you have a scene where a character's moving around, they have clothing and they're interacting with cloth, you know, the sheets and so on. They're coming on the bed, off the bed. And then at some frame in the middle of this animation, there's this shot, right? And nothing in this scene is by accident. You know, the way the cloth is exactly at her knee line, not too high, not too low, and is you know, moving when she comes on and off was on purpose, right? So how do you make sure things do what you want if you're working with a physical simulator? Usually you start integrating with initial value problem, things go, and then you get what you get, right? But you want to control things, so you need to have a system that allows you to work with it interactively, essentially. And people that made this shot, the TDs, you know, have to do all kinds of work to design forces and ghost forces to push things just right, and then they change the resolution and hope it works better for the final shot. And this is really hard to do. So if we want interactivity and high quality, these are, you know, there's at odds. So there's no free lunch, but what we want to do is be able to build a tool. Initially, I'm going to talk about quasi-static simulation. So things like draping a piece of cloth. Maybe you want to explore different materials, things that are thin, have nice buckling and creases like this, or maybe you want to, you know, change the materials as you go and move things around. So this is just, initially we're going to talk about quasi-statics of cloth, things that have a flat rest shape. And so how do we think of progressiveness in graphics? So there's all kinds of paradigms for progressive simulation. So on the left is like 3D rendering, right? Monte Carlo, path tracing. You can render things at coarse level and then refine it and get more detail as you go, right? And on the right, we have progressive meshes, progressive geometry, where you can have a mesh, you can simplify it, and you can build a hierarchy of meshes, and you can refine along the way. But this isn't like, you know, this isn't solid mechanics, but these are ways people work with progressive representations. It's super useful level of detail, make things fast. You can see results right away. You can try things out and then change things if you don't get you would like. For level of detail, the current state of the art of things like Nanite system and Unreal Engine 5, which uses all kinds of really fine meshes at different levels of detail, and you can change these on the fly. Artists, you know, experts in fluid simulation, you know, they use little strokes of paint to get the background, and then they add more detail in a progressive way. If you work in solids, you know, then, you know, you may sculpt things in a progressive way to get details where you want them. So how do we do this for cloth simulation? And I want to emphasize that this is different from just the idea where you simulate things at a coarse level and then you get something and then you simulate in a fine level. And in the limit, you know, given some epsilon, I'll tell you a delta and you'll get an accurate result. We're not trying to do refinement in a progressive way to a limit solution like you do in numerical analysis. We're actually trying to progressively refine a thing that we're working on, which maybe is different from the limit case. And this is a really important distinction. So for example, here's a typical problem with direct simulation. So you say, okay, I have to make this shot. I'm going to throw this blanket on this guy, and you simulate a cloth being put down at a low resolution, and you get this result. You say, oh, I like this. It goes under his chin, and I don't know if you can see my mouse. Can you see my mouse? Yep.
Yes, we can.
Yeah, okay, great. So it goes under his chin, and he's got these nice wrinkles. This is what I want. And so then you change the resolution and rerun the simulation and wait a long time, and you get this. And this is typical because now you've got something that just doesn't do the same thing. It's you know, it's got fundamentally different wrinkles. It caught on the guy's nose now, so the shot is ruined. So if you run something at a low res and get something you like, just increasing the resolution doesn't give you something consistent necessarily, right? In some cases it may, but in a lot of cases it doesn't. So everybody who does fluid dynamics knows if you run, you know, smoke at a low res and you get something that goes, looks nice in this way. If you run at a high res, it may do something totally different. It may have, you know, all kinds of more vortices and so on. And that's what you want, you know, if you're designing something or trying to do predictive simulation with fluids or solids. But for art-directable physics, you want to direct something quickly at a low res and then refine it in a way which adds plausible detail, but doesn't necessarily do something more accurate and different. You want it to be consistent. So this is the fundamental challenge that we have to deal with. Okay, so moving along, another challenge is cascadic methods are a natural approach to this. So what they do is they basically say, I have a coarse sim, it's doing something I like. Now what I'm going to do, so I'm say draping this piece of cloth on the left. I'm going to now prolong it to a finer mesh, and then use that as an initial guess for the next phase of relaxation, say of this fine level simulation. And this is kind of like warm starting the quasi-static solver. And this, this is a reasonable thing to do. But the problem is the coarse model is garbage, really. And so whatever kinks and creases and locking artifacts this, coarse cloth or shell model has are going to be inherited by the warm start to the next thing. So now you've got this fine level cloth model, which if it was simulated directly would give you something nice like this. But now because you warm started it, you baked in these creases and locking, the thing is not in a very natural state. And this is typical of these kind of methods. They're useful for interactive design because they allow you to work coarse and go fine, but they have all these problems. And so what we really want is a better coarse model, a smarter coarse model that is also consistent with the finer scale. And then people often, multi-grid and multi-level methods are related to this, but they're for, linear solvers or say nonlinear solvers, but they're not fundamentally for progressive art-directable physics. They're just solvers, right? But we can use them too, but they don't solve this problem. Okay, so the next thing I want to talk about is just like, how do we get interactive high quality cloth? Well, the basic approach to this is progressiveness. We're going to get both of these by using a progressive approach. And this will also give us control. So we're going to start with a coarse sim and build, in this case, a quasi-static simulation. So we'll pose the cloth in some way on a coarse scale. And then what we can do is progressively refine the simulation to get something better. It's not the same thing, otherwise why would we just do that? It's going to get more detail and more, finer wrinkles and things like that, but it's still going to be consistent with what we had. So the rough shape of it will be consistent. It's not going to fundamentally do something else or pop out or fall down or whatever. And so this will give us a consistent representation across scales. And it's also, the simulator is reliable. So we're going to use a rock solid simulator. We won't allow any intersections or artifacts. And it's going to come at a cost, but we're going to pay the cost of the fine scale and work quickly at the coarse scale. At any point in time, you can interrupt the simulation as it goes from coarse to fine and change parameters or work with it, and then it'll just go back, and you can keep doing this over and over again. And then, of course, the key thing is that we'll have interactive previews at every stage of the process. So working coarse, we'll always be able to see what's happening, and then we can refine it. So that's the basic idea of this original PCS method. And so here's the idea of consistency. So at level 0, we have something like this, but as you refine it, the simulator gets more detail. You can see that the quality of the folds are finer and more resolved, but the thing is not fundamentally buckling or creasing in a different way. It's doing something that's similar. Maybe you could argue this is not the most exciting example. It's just like a handkerchief on a ball, right? Nobody's gonna, go to the movies to see just this, but it's something that, is clearly consistent in space with what's happening here. Like you could measure the curvature and define some measure of consistency, which we did. The other thing you do is you can change the materials as you go, right? So a cool thing about this is that you can, work with one material and then decide you want to change it and get results for that too. So if you can be working at a coarse scale and then try out different things and rapidly explore the space of possible materials and outcomes, which is what you want to do for design. The other thing is that we can avoid the artifacts of coarse direct sims because, okay, so on the left here, we just have a cloth model that's simulated on this mesh. And what you see is what you get. It's simulated in some it's basically solving a statics problem with a Newton solver, and you get something like this. But it has a lot of artifacts that are representative of the kind of failures of just really coarse cloth mesh models. And whereas this one here is smarter. And the reason it's smarter is basically because the coarse model that we're using here is doing multiscale model reduction. It's basically using elastic forces and energies defined at the finest level mesh, and then restricting these down to this. So it's using a much better shape model for its elastic energies. And so this thing behaves like it's actually a finer scale model. So it comes a more of a cost to do this, but it's better than just using the coarse model itself. And the other thing is that this model, because it knows about the fine scale energies, will, when you refine the mesh, still behave in a similar way. So that's going to allow us to have consistency across scales, because the coarse model is actually, knows about the fine scale model in some specific ways. And when you refine the meshes, then you get something here on the right, which is consistent with what we had on the left. Okay, it looks similar. Whereas the one on the left is got some different artifacts, things move around, and it's not as consistent. But also the other thing is that when we refine this and solve it at the fine scale, it is actually a converged Newton solution. It corresponds to a, approximate minima of the energies. Okay, let me see. Okay, so this gives us speed up over a direct simulation. So here we can drape the PCS simulation at a coarse scale, and then when it gets to its relaxed position, then refine it. And this is better than just directly working with the fine model itself, because this is just going to take a longer time, because it's basically just time stepping lots of these degrees of freedom in the Newton solver. So working coarse is much faster, and in some cases it can be arbitrarily fast because you can't actually get the work done if you're working at a fine scale. So this is a sped up a session of somebody working with the system to build an example I showed you in the very beginning. So there's a bust of a character, and then this piece of cloth is being draped over it, and then interactively manipulating it to produce what you want. So like the typical design process is, you don't know what the final outcome is. You're trying to work with the system and the media to figure out what's possible. So they're changing material parameters, and then they're also changing the configuration and moving things around. So in this case, you can translate, rotate, and scale the collider, and the system pushes it out in this case because you've specified some infeasible state. And then grab it, you can basically grab the cloth and move it around like you would in a typical system. And in this case, the person is trying to move the cloth around the character. And so this is the system. And so then as you get closer to your goal, then you can go ahead and refine the actual resolution. And it gets, of course, much slower. But by this point, the person's done. So the artist has basically found something they like. They've increased the resolution, and then they just wait for the higher quality result to come into play. But all of the design work is done in a more rapid prototyping coarse scale. Okay, so here's the final result. So this is what they designed, and it's only 1.5 1,000, 1,500 triangles, and this can be solved very quickly with a direct solver basically. And then this gets refined, and the end result takes much longer, but you get something that's consistent. You have to wait, but you don't have any anxiety. You just have a coffee and relax. It's going to work out. And here's a final render of that draping design. So if you tried to work directly on the fine sim, it would be too slow. If you didn't work on the fine sim, you just worked on a coarse sim, it wouldn't be consistent. So this solves both those problems. So the basic idea of the method, I should keep an eye on the time because I'm going to run out of time here. So the basic idea of the method is you basically want to take the cloth in some initial state and then get to some final converge state. You have a coarse preview, and then you can progressively refine this across levels in a way that preserves the integrity of the simulation, doesn't introduce intersections or artifacts. So this is done in an incremental potential formulation. So we're basically minimizing some energy of the system, where you have membrane and bending energies of the elastic simulation. And then you have this contact, a barrier for contact, friction, and then a strain limiting potential, this is sort of incremental potential contact formulation. And this will guarantee things don't interpenetrate, and it's solved using Newton with line search and some robust solver. And it may take a long time, but it'll get there. And in order to deal with the resolutions, we have a prolongation approach where you basically have this mesh, and it's basically subdivided or prolonged to a finer mesh. And then at each level, basically, you essentially want to solve this problem where there's a level L, you have some energy for that level, and then you could just solve each one of these separately, and it would kind of look like this. You know, each one would have a different minima. And we want to relate them by this initial guess, X bar, which is basically our warm start. But we don't want to do this exactly. So the problem is, if you just solve each level's energy separately, then you're going to have some problems. The other thing I should mention is that in order to make the process coherent in time for somebody working with the system, we have a sort of pseudo time by adding an extra, basically, penalty term, which corresponds to like this kinetic energy thing. So you have a mass norm on the change in position, which basically produces the kinetic energy type energy in the system. So the problem I talked about before, where you take a coarse model and then you refine it and use a warm start with this, will give you artifacts for membrane locking, because the coarse model is a bad model, and it's going to put in artifacts that when you refine as a warm start will be hard to undo. So if you like crease or knot up your simulation, the cloth is going to have a hard time undoing that, and it may just say, fine, I'll just stay here. But it's not a natural state for the cloth to have these mesh artifacts in it from a coarse scale. So instead of using each level separately, what we're going to do is we're going to use the fine scale energies at the coarser scales. And so in order to do that, we have a prolongation operator, which basically refines a solution or a vector from one level to the finest level. And then what we do is we evaluate the contact energies for the barrier, friction, and strain limiting at the specific scale for the mesh you have. But the membrane and the bending energies are going to be for the finest level. Okay. And this will make it behave much better, it turns out. You could do these at a finer scale, but it's not worth it, it'll turn out. So this will have good contact handling constraints at the current level for this specific geometry, and then we'll refine basically and evaluate the energies here, and those will get restricted back in a usual multiscale model reduction kind of way. And so in this case then, right. So this gets all put in a Newton solver, and in order to solve this, of course, you have to compute derivatives and Hessians and things like this, and so this can get expensive. So the gradient of the energy is just the forces on the system at the scale, and then the Hessian involves two parts. The first part is going to be, the mass matrix, which is just there for keeping it from, just for coherence. But then we have the potential, the gradient of the energies at the fine scale for the elastic energies, and then the contact Hessian. So this one is easy because it's at the current level, but this one involves fine scale information. So there's the usual kind of, how do you evaluate the stiffness matrix for this reduced system using the fine scale model? In this case, because we're just doing a Newton problem, we could do an inexact Newton solve and just use this Hessian at the current level. And so this is a simplification which will speed things up quite a bit. And so then the Newton set proceeds, and if it's done right, you get to a reasonable feasible minima. And this is what the system does. And then in order to get to the next step, you just keep doing this incrementally, and then you converge to the solution. The one thing you have to watch out for is when you change from one resolution to the next, you can mess things up by changing the contact state. So we have to make sure that there's an intersection-free upsampling that happens. And so we do this by doing basically a polyhedral subdivision. We just refine the parameterization, not the geometry. And then we do a continuous collision detection to basically allow this thing to relax and take its natural state. And this can introduce intersections, but this is, if it's done properly in this way, then we're able to, make sure that we don't mess things up. And it has to also work for strain limiting, because if you allow things to get pushed around as they change from one resolution to the next, you could introduce a lot of energy by stretching something that doesn't want to stretch. And so that energy has got to be satisfied too. So there's a whole tedious sequence of steps that allow us to do this, but we can change resolutions as we go. And then if you want to go back and fix things, you can. And so this is the interactive workflow. Okay, how am I doing for time? So there's some consistency with the curvature. If we look at mean curvature between levels for our model versus previous cascadic approaches, we basically win in every scenario that we looked at in the paper. It's just more consistent. And we can also have nested collision geometry, not just a cloth, but we can have progressive representations of scenes that allow us to refine the geometry of the scene as we go. So this helps with speeding up collision detection, basically. So here's a gallery of some different simulations that were made, changing the bending stiffness, the materials, and then here's an interactive workflow. So after 9 minutes of working with the simulator, which is not much time given that to do the solve, it's about that time to actually do one solve, right? Or so you can't work at the fine scale. If we work in a progressive way, we can get the work done. And here's a larger scene. I'm just going to sort of speed this up, but somebody's working with the system at coarse scales, and there's multiple layered pieces of cloth that are sticking together, and the thing responds in a coarse way, and then when you stop moving things, it starts refining and adding more detail until you change it again. So it's a fully responsive system. This is a prototype, it's not a product, but you get the idea. And then you have multiple pieces of interacting cloth, and in the final thing, you have as many triangles as you want. Okay. So this is just for cloth. The next part is for shells, and I want to go through this more quickly because it's more complicated, but basically these have non-smooth rest states. So they have geometry that when you refine them, they're not just a flat piece of cloth that's bent. It's got some inherent non-zero rest angles for the shells. Shells are interesting. They have all kinds of interesting behavior, but they're more expensive to simulate. So the usual problem of speed versus fidelity is even more interesting for shells. So if you try to use a really coarse simulation, you'll miss all these fine details and buckling effects that you need a resolved shell simulation for, and you'll get all kinds of locking effects. So I'm just going to speed this up. So here's like a direct simulation at a coarse scale. You get all kinds of artifacts. It's just terrible. So how do you get this with a shell simulation? The same sort of thing we did before only works for subdivision connectivity, which also it's subdivided a flat shape to a flat shape. But now with a shell, now we can do subdivision surfaces, but there's no details. How do we take a specific detailed mesh and work with it in this way? We can't assume it's a subdivision model. So we want to take arbitrary fine geometry and then build a hierarchy from that and use that in a progressive simulation framework. But this is difficult because it's not just a repeated subdivision. Everything's not in plane. Okay, so this is where this method progressive shell quasistatics comes from. Still quasistatics, but we take a high resolution model and decimate it using like a quadric simplification class of method, not that one exactly. And then from that, we have a hierarchy to refine it. And so here's a simulation that somebody's working with a coarse model on, and they can, pose this character however they want, and then refine it and get the simulation corresponding to that. This is like a shell balloon character that has some details. Okay, so at level 0, you get consistent solutions as these things evolve, and you get extra detail and geometry that gets added in. It's not just a smooth limit surface. And it's just fundamentally better. So the progressive simulations coarse model is smart because it knows about fine scale energies. So when you refine it, it's consistent as well. And it avoids locking artifacts. And we can upsample the contacts. So here, as we add more detail, we don't get interpenetrations. And even in this pretty challenging case, things just resolve and work. And so you can do something at a coarse simulation scale and then keep increasing resolution. The contacts get resolved and there's no interpenetrations and everything, just works. The details of it are fascinating, but also they're going to cause me to run out of time. Let me see. So we're going to do quasi-statics again. What we really want to do is dynamics. That's the next paper before the bubbles. So let me just speed this up a bit. So previously we did quasi-statics, but now this only works for subdivision connectivity. So the thing we have here we have the coarse level proxy energies using fine scale elastic energy. And then we have a safe initialization, but this only worked for in-plane stuff. So we could assume that we just refined the triangle in plane. So now we can use the simplification to get a coarse model, but to refine it, this is a problematic thing. And we also have to make sure that when we prolongate it, we don't introduce interpenetrations, which is now harder. And so those are the two things that this paper does. There's some prior work I want to skip that doesn't solve, it messes things up and adds ghost forces. I skip this. And this one, it makes the things dense. So we want a fast and sparse prolongation. So this is based on edge collapse. And the basic thing is that when you want to add an extra degree of freedom back, you can do it in the plane of the triangle using a barycentric intrinsic coordinate, but you still need to go out of the plane to inflate the shell. And this is the extrinsic prolongation part. And so as we do this, we basically track a local frame of this triangle and figure out where the barycentric coordinate of the coordinate is, and then we add an additional displacement off this in the local frame. And this is how the prolongation works. And we show that this actually works and it's stable and gives us good energies, which is the key thing for simulation. And so we're able to then prolongate this and add detail, and the system will work. In order to initialize it, we need to make sure that there's no interpenetration introduced. And so in order to do that, as you add more degrees of freedom, you have to check for collisions when you're doing these edge expansions so that you maintain a feasible simulation with no interpenetrations. And there's some details about how this has to be done in a robust way, because you could have things which are like, a coarse shell model, which is like some origami, satellite thing all packed in, and then you want to add degrees of freedom and there's no room. You have to make sure that this is done robustly. And so there's a part of the paper which is dedicated to this part to make sure that you can inflate things in a way which is done safely. And I won't get into this. There's a randomized search method that guarantees that it works. And so if you use this, then you're able to deal with challenging cases like the one we saw where you're twisting the cloth. You can twist it right up and it will still figure out how to inflate this thing and not introduce any interpenetration artifacts. Let's see the paper for details. It's also parallelized by figuring out local regions to do this. Okay, so once you do that, then you're able to do prolongation with these models that preserve the classic shell energies for symmetric inversions. They're better than the previous cloth approach because they have a better approximation of the energies at finer scales. They don't have parameterization artifacts as much as loop subdivision did. And so they just do a better job of coarse approximations to the model. And then when you refine them, they're better. So here's a shell model with a crush example. And then as you refine the simulation from here, you get something that's consistent. This is a whimsical example where you're simulating at a coarse scale and then refine it, and you get something consistent. Another inflation example. And let me just keep moving along and run out of time. Okay, so for animation, this doesn't address animation. So previously we just looked at quasi-statics. And in this new work, basically we can actually add the dynamics back in. So here's a good example where you have this character, you want to throw them through some hoops, and you're working with the simulation. It's incredibly slow. This is a real-time capture, actually animating this character in Houdini, and it doesn't get through the hoops. So you say, oh, I need to increase my velocity, or I need to move the hoops, or something like this. So it's very tedious to get these things done. But after some work, you eventually get the character to fly through the hoops. This is using Houdini's Vellum simulator. It's a position-based dynamic simulator. But as you increase the resolution, the simulator changes behavior. So we go to the next level, it does this, and you go, oh no, I just spent like an hour getting this guy to go through the dang hoop, and now, it doesn't go through. If you let it go up another level of resolution to the full model, this solver isn't like consistent across scales. This is, a kind of absurd example. If you had a better simulator like IPC or finite element shell model, it would have less variation, but it would still be different. And so what you can do at one scale, we can refine quasi-statically, but how about dynamics? How do you refine dynamics and still get something that's consistent across scales? And this is what the progressive dynamics work does. You simulate something at a coarse scale with an enriched coarse model with this multiscale model reduction smarts to it. And then when you refine it, you're going to get something that also produces qualitatively similar behavior with now more detail. And so he still bonks his nose in the way the animator wanted. And as you keep adding more and more detail, you get to the final simulation. So this can run, offline, but you'll be sure that it's going to produce something consistent. It's not the same as doing the original fine scale simulation because it's biased to be consistent with the coarse scale model, right? So this is the key thing that gives you control. And so this works for scenes like this one, which are really complicated. On the top right, here's these whimsical sky dancer models where everything gets designed at the coarsest scale so that it's got the right materials. If you've never made one of these animations before, maybe you don't know the wind speed to use to get these guys to jiggle and dance in a fun way. So you have to explore at the coarse scale, and then you can refine, and you'll get something that does the same thing, not like blows like crazy or stretches too much or falls on the floor, right? So you get consistent progressive dynamics. Okay, so I don't have time to talk about the details of this, and this work is just coming out at SIGGRAPH this summer. So check out Eris's webpage for the progressive dynamics work that'll be out shortly. And that's it for this part of the talk. There's a whole bunch of other results that show, basically you get a flag model that's consistent across scales. Whereas if you did a full simulation, just a regular shell simulation in orange here after this one, basically you get something that diverges. The simulations at different levels of detail don't do the same thing, which is what you'd hope, because otherwise everybody just do everything at coarse scales. Okay, so that's the end of that part of the talk. The next part of the talk is this one. So I've got just a little bit of time for bubbles. Let's see. Maybe I'll just keep the questions to the end. Otherwise, I'll run out.
Oh, take your time, Doug. Yeah.
Okay. Okay, so the last part, I just wanted to show you some cool work that Congre, along with other collaborators at Adobe and Stanford, that we've done on making water sounds better. So I'm super excited about sound synthesis in general, and then water sounds. But here's an experiment we did back at Cornell where we recorded lots of droplets and bubble sounds. And the basic problem is that when a bubble is created, it vibrates very strongly due to compressed air and the energy of the mass of the water, and it can produce notable sounds. In particular, so basically have bubbles that have a frequency that's inversely proportional to their diameter. This has been known for almost 100 years, and so small bubbles, produce these classic, musical tones in isolation. And this can be used to make sounds. But people have studied bubbles and their properties for how the frequencies depend on shape, how they may couple together has been explored more recently. And there's this great book by Tom Layton called The Acoustic Bubble, which talks about all kinds of things. And people care about this a lot because for remote sensing, for climate models, understand air, ocean, mixing effects is absolutely critical to so many things we do. In computer graphics, we had a paper back in 2009 that looked about how to use bubbles to make sound for animations. So we produced various bubbles using a stochastic approach where we would look at how some particle level set or particles near the surface would get mixed into the fluid, and then use that to generate bubbles in a stochastic way, and then just use the inert bubble frequency just based on the 1 over the diameter of the bubble. And this tended to make the sounds pretty shrill. Like we ended up with a lot of high-pitched sounds. It was kind of harsh. Early sounds always bad, but it gets better over time. And then so follow-on work by Moss said, look, they only use this pulsating mode of the bubble. There's these higher oscillation modes, but these tended to also introduce higher frequency sounds, which made it even more, shrill, essentially, in my opinion. So this doesn't really solve the problem. And then in order to figure out how to do better, we went to full two-phase flow simulations where we had incompressible bubbles. And this, was computed with a simulator called Eris, which was very expensive, ran a supercomputer. And we got these more higher fidelity water simulations and to see, does this make it sound better? And so this was a lot more expensive. We also had a solver to figure out the bubble frequencies based on a capacitance solver of associated Laplace problem. And we get things like this. So here's what they sound like. So all of these are, have some watery, bubbly character, but they're missing something, right? One thing is that the frequencies are just generally too high. There's the other aspect of the radiation and the transfer in the air domain, which I'll talk about a little bit later. These ones on the top include it, this one on the bottom ignores it. But the problem that we had is a lot of these frequencies are just higher than we observed in practice. And one thing that is happening is if you consider a bubble oscillating independently, it has this damped sinusoid kind of behavior. But the frequencies are much higher because when this bubble is pulsating, the coupling with the neighboring bubbles has been ignored. But in practice, if you include coupling, then you get more interesting variations in this instead of just a ping of a damped oscillator like we had before here, which is kind of digital and shrill. Having this coupling gives more interesting fluctuations in the waveform. And it also introduces more effective mass in the systems. The frequencies are lower and it produces lower frequency sounds, which is really fundamentally important. When you go to the ocean and hear a giant wave crash, the bubbles are really tiny. If you played them all as independent oscillators with the 1 over diameter frequencies, it would be just shrill and loud as can be. But when you introduce coupling, the ocean gets lower frequencies and roars. And this has been known in acoustic bubble community for some time. So here's this example by Leroy where they basically couple a small number of bubbles together, and you already get a reduction from 3 kilohertz down to, like, 2 point whatever. And in practice, if you have, like, increase the number of bubbles in some test volume by a factor of 1,000, you can get a 10 times reduction in frequency. So that'll get you from 2 kilohertz to 200 hertz and gives you a low frequency roar. And so this is the key thing that we want to include, and which was missing in all these previous works. So in this case, we have an uncoupled simulation on the left, which is coming in, and you get something like this in the spectrogram. And on the right, we have a recording of a different but comparable scenario. And what you have is this lower frequency lobe that comes in. You have the stuff near the surface, which is splattering, increasing as it pours, fills up the glass, the resonance increases, but you have this lower frequency effect, which is, we argue, due to coupling. And so this is what was missing before, or one of the things that is missing, and we want to look at that. And so here's a preview of our results. I argue that this is fundamentally better than what we had before. This is being computed with the coupled bubble oscillators, but also the sound radiation is doing a time domain wave equation. And here's the previous uncoupled results with the better wave equation. So as it pours in, the bubbles just all sound the same frequency all the time. They don't have the variation in the pitch. And so you can see this down here. You can see this coupling adds this lower frequency lobe, which we were hoping to get. And at any point in the simulation, you can look at the modes of oscillation of this bubble cloud and see what's going on. So the low frequency mode is lower than any of the individual bubbles by quite a bit. Okay. So these simulations were, how am I doing for time? I'll try to hit the time. So these simulations were computed using Houdini, which is an animation tool that is used in industry. So this is like a flip simulation, which is a fluid implicit particle simulation. So it's a single phase flow. The bubbles are created using a particle-based model, which stochastically creates bubbles, and they split and merge in some procedural way. This is very ad hoc. So the sound quality is not coming from the fidelity of the simulation. This is a very low fidelity particle simulation of bubbles. In this glass pour example, for example. And then the coupling is basically the thing which makes it sound good. Okay, so we introduced a practical framework for simulating coupled bubbled sounds. It involves a coupling model based on the mass matrix and an efficient way to compute airborne sound on the GPU. Just to give you an idea, so the basic model of a bubble is just an independent oscillator. So in a pressure volume frame, we have forcing due to pressure, and then the volume fluctuations of this bubble are modeled here as this V. And then, so this is a simple harmonic oscillator. If you have a bunch of bubbles, they're all decoupled simple harmonic oscillators. And when you introduce coupling, the pressure from one bubble can drive the other bubbles, essentially. So as you know, it changes its volume. There's some incompressible velocity field that causes pressure changes elsewhere. And so this introduces coupling. And if you symmetrize the system, you end up with a mass matrix formulation, something like this. So you basically have off-diagonal entries in your mass matrix coupling these bubbles together. So this is a weird system. Usually we're have like used to a sparse stiffness matrix, but this is basically just due to the gas in surface tension. So it's diagonal, and you have all the off-diagonal coupling in the mass matrix, which is a bit awkward because if you want to time step this, now you have a dense matrix. So the coupling is smaller if they're farther away, but bubbles come and go. So you add a new bubble, you have to increase the mass matrix size. If it pops or something, you have to decrease it. So this introduces changes in this, and then you have this problem that you have to time step at really high rates. So this is an awful space to be in. Like even if you want to do forward Euler time step or some, midpoint, you'd still have like a dense matrix you have to solve to do an explicit solve method. So this is awful, and tiny time steps. So the way to deal with this, we factorize the mass matrix with Cholesky, and then it's positive, definite. We can interpolate the inverses and they'll still be positive. So this is good. And so this allows us to interpolate these factorizations along the way to make something go fast. The matrix can still lose positive definiteness as bubbles get closer. It's not guaranteed. So we regularize the symmetrized mass matrix, and we can show this fixes it. And then you can also do low rank update tricks, which is fun. So here's like a reproduction of this classic example where they have a bubble net, and then you can show the modes that this system produces, which correspond to what was observed in the previous approach experimentally. And these are the modes of the bubbles in the glass example, showing a pretty low frequencies for this bubble cloud, the lowest mode, which allows it to capture these interesting effects. The last part is just how to compute the sound in the air domain. We don't listen to eigenvalues or bubble frequencies. We hear air pressure fluctuations. So we took the previous approach where we had like a time domain wave solver with basically cut cells and ghost pressures, and then we basically put this in a GPU wave solver. But the problem with this is that how do we do this on like cut cells and things like that on the GPU are really hard to do. So what we're going to do is we're going to basically simplify the way we evaluate the pressures. We're not using the boundary data. Sorry, I'm trying to go too fast here. Basically evaluate the surface accelerations using a simplified model. And then in order to compute the pressure in the air domain, we use a sample and hold approach to basically solve the waves in the air domain. And this is because there's so many abrupt changes and popping artifacts. The previous solvers were just not robust. They would die, or they would introduce artifacts even if they work. So what we did is we basically just freeze the geometry at certain times and then use the boundary condition model to evaluate the boundary data on these frozen geometries. And then we use this parallel in time approach that we came up with in our previous paper, where we can for each of these sims, they basically generate some non-zero data and get a sound clip, non-zero data, sound clip, and then we sum all these together, and then we get the sound to each of these instances in time. It's just like a frame-based sound rendering approach. And so each of these frozen geometries can use just a fixed geometry in a GPU solver, so it's really fast. And then we sum these together and get the sound. And so we get a significant speed up, and it's a much simpler implementation over the CPU implementation. This is running on a cluster in the cloud. So this is much more expensive than it looks, but even still, it's just much faster, even on one GPU. Okay. The coupling simulations are on the CPU, but they're just doing Cholesky, and so it's very cheap even with this number of oscillators. So here's some results just visually. So as we add coupling, we get more low frequency lobes in these things, more low frequency character. It pushes things down, which makes it sound a little better. And for example, in these pouring examples, you get these lower lobes of low frequency content, which makes it better. So I encourage you to go look at the videos online. You can see these and hear them at higher quality than you can probably see over this WebEx call. So here's the pour example. And from a simulation, it has similar character to a recording, although recordings are always better and different for all kinds of reasons. So anyway, so adding coupling and improving the efficiency and fidelity of the radiated sound is our areas that we can improve. So in the end, this adds more low frequencies, makes things sound better, and makes things faster too. And in future and ongoing work, we're still improving this and making it more practical. We want to be able to do all these kind of effects and make it easy for people to author them, but also not just do water, but everything as well. And so our current approach is like how to make a unified GPU solver which supports everything and doesn't suffer from all the complexities of meshing and interface boundary condition handling. And yeah, so I think that's it. I'll just end here. And if anybody has any questions, I'll be happy to answer them. So thanks so much for having me, Young-Soo.
Thank you. Thank you so much for the wonderful talk, Doug. Okay, so let's have a Q&A sessions. Does anyone have a questions? You can unmute yourself and then ask questions. Mike, I have one question. Okay, the first part of the talk, you talk about like going from coarse to the fine scales and, the cloth animations, that was the method was applied. I was wondering, because a lot of simulations we are interested in is like actual fracture or the crack propagations. Those techniques, how can be extended to those, actual tearing and not only the, the bending.
Right. Yeah, I think, yeah, so extending the progressive framework to fracture and things like that is,
Yeah.
it's kind of the part of the question is like, what does that even mean, right? Like, I think, if it's a dynamic process, then extending it so that you can tear things in a coarse way and then refine them and get more detail.
Right.
I mean, that would be a natural thing to want to do because the process is very expensive. And it's also often people have artistic goals or I think a lot of the way people deal with artistic goals or fractures, they have fracture patterns that they impose, or they have like enrichment functions where they try to make it satisfy certain types of interface displacements and so on for the fracture. Yeah, I don't know. I think that's an interesting thing. We're interested in Eris, who's actually in the call. She's done a lot of work on trying to extend progressive quasistatics and dynamics to support volumes and other effects. So doing fracture and all these other more complicated phenomena is definitely something we'd love to be able to do. But it's lots of open questions with geometry for sure.
Got it. Okay. Shaima, you raise your hand. I'm guessing you have a question.
Hello. Thank you so much for the presentation. So I can also maybe switch on. Yeah. So thank you so much for the presentation. It was really amazing. I enjoyed it a lot and I learned many things today. I have a question about the consistency measures of the methods because I also am a PhD student, work with the reduction methods for physics-based simulation for computer graphics, and what we usually do is that when we have a reduction method, then we compare to what the full order model solution will give us, and then we have this error measure, let's say, compared to the full order model, what it does. But you explained, you showed us that sometimes when you have the very fine mesh, it does not give you the same behavior that you want, and like this sticking on the nose of the armadillo mesh that you showed us at the very beginning. So I was surprised that a finer mesh would not maybe give me the solution that I am aiming at. So if you can please elaborate on the consistency measures, because that would be the main measure. And one more thing that is related to the same question, because you also showed us that when you change the refinement level of the mesh, it changes behavior. So that was just like the hoop jumping example. Then how do you control the coarse level mesh? Where do you start from so that you get the level of details or the behavior that you are aiming at in your simulations?
Okay, yeah. So there's two things happening here. So on one hand, there's like the traditional refinement problem that predictive scientists like yourself have, where you have a simulation model at some discretization level, you refine that, make that smaller, and it converges to this true solution, right? That's that's a well-founded, consistent stability, convergence, all that stuff we know and love. The thing with progressive simulation is, as you, in that model, as you refine the mesh, you get just different solutions. It gets closer to the true solution, but it's not maybe what you want, right? Because you want to design at a coarse scale and get something that you like and then refine it. But as you refine it, it may do something different, just that's the way physics is, right? And so the whole trick of the progressive formulation is to make the coarse model more expensive, albeit, because it's using some things from the fine scale, but not everything. It's not a full fine scale thing. It's still doing a low dimension. The matrix problem you solve is still small, like in dimensional model reduction. But it has some energies from the fine scale elastic part, which make it think it's doing something better. Okay. And so that allows it to behave more like a full scale model, so that when you refine it, it's still predictive enough that it behaves in a similar way. But it's not basically allowed to converge to the full thing for example, in the dynamics case. And so it's biased. The coarse model is better than just a regular coarse model because it's using fine scale energies, but it's biased in the way Eris is doing the optimization for the time stepping scheme, because it's trying to balance two things for the dynamics, for example. The dynamics is balancing one where it's just going to take a coarse simulation and then prolong it, refine it so that it's just going up. If you do that, the coarse sim will be prolonged and every frame will correspond and look great. But when you play back that fine scale animation, it's going to pop and jitter. It'll wrinkle this way and that way. It's going to be incoherent in time. The other scheme is just to say, well, I'm just going to, prolongate the initial thing and then run all the simulations at each level independently in time step them. But now it'll be coherent in time, but they'll be divergent across scales. So what the progressive dynamics approach does, it's an optimizer for the times. It's basically formulates the time stepping scheme as an optimizer, which balances two things. One, how you're solving, say, backward Euler in time, but also it's balancing how it relates to the coarse scale. Basically, it's using an initial guess that's related to the coarse scale. So it's balancing the errors in temporal dynamics, momentum, and it's balancing errors in refinement across scales. And if it does that right, then you get this whole space-time, framework, which is smooth and coherent. And but it's not predictive, right? It's not like an accurate simulation, like you would refine it, because it's going to be biased to the coarse model. So you pick a coarse model which is good enough, but still fast, and then you can refine in this space-time framework.
Yes, and the bias term is this a strong connection to the coarse mesh between the fine and coarse mesh, the penalty term that you introduce to the energy, I guess, with the norm x minus xp, something like this.
Yeah, that is basically.
This is what makes the.
No, so that term, the difference in the changes in the position in a mass weighted norm, basically just like you can interpret that as just a kinetic energy model if you look at like a position-based formulation of backward Euler in position-based optimization. So that's just kinetic energy. The thing that is for the progressive dynamics to work in a coherent way is in the paper, which Eris is going to put on the web any day now, I'm sure. So check
Looking forward.
Yeah.
Looking forward.
Great. Thank you for your questions.
Thank you.
All right. Thank you. Thank you so much. Is there any other questions? Well, it's 9 after 10, 9 after 11, so.
It's probably good. But
yeah.
And if anybody has any questions, feel free to reach out to me or either of my students, and I'm sure they'll be able to answer your questions.
Yeah. Thank you.
Thanks so much for having me, Young-Soo. It's great to see you.
Thank you.
Bye-bye.
All right. That ends the seminar today.
Great.
Okay. Bye-bye.
Bye-bye.